Last time we finished up really chapter 2, and again we did talk a little bit about one topic from this chapter, chapter 3, which is electronegativity. And as we talked about yesterday, um, really the only thing you need to know about that for the exam that's coming up next week is just basically what electronegativity is and its general trend. Again, just to sort of relate it to all the other sort of periodic trends that we talked about yesterday. We obviously are going to talk about electronegativity as well in this chapter. We'll go into a little bit more, I guess, detail, I suppose, and obviously you'll learn that stuff for the next exam. So, again, really the exam that is coming up here, I guess, on Monday. We'll cover really chapter 1 and chapter 2, pretty much most of it. And again, just a little bit of electronegativity in terms of general trend and sort of relating it to the other periodic trends that we talked about. So what we're starting here, again, just to be clear, is not going to be on the exam on Monday. This will be exam 2 material here. So from this point on, pretty much what we're talking about for the rest of the week, obviously, and on, we'll go to exam 2. All right, so we're going to start talking now about, now that we talked about sort of the atom in the first couple of chapters, we talked about electrons. We're going to talk about sort of those electrons now in terms of bonding. So we're going to talk here in chapter 3, and then really in chapter 4 as well. They really kind of go together. They're sort of the bonding chapters, if you will. Sort of this is kind of the first bonding chapter, and then chapter 4 is the second bonding chapter. So here we're going to talk about all the different types of sort of bonding. And again, there's ionic bonding, covalent bonding. We're going to talk about drawing Lewis structures. And then chapter 4, which comes next, kind of ties in the rest of the bonding. Again, everybody's favorite geometry. We'll also talk about hybridization and some other things. Again, that may be a little bit new to you, and some of the stuff you may have seen before. But again, we may go into a little bit more detail on some of the aspects of this that maybe you have in the past. All right, so chapter 3, which is bonding, and I know it says covalent bonding, but we're really going to talk about all types of bonding here in this chapter, just to make sure everybody's sort of on the same page. So really, when we talk about bonding, the very first sort of thing that we usually come across or sort of use to help us understand bonding or sort of represent bonding or chemical bonding are Lewis dot symbols. Sometimes they're called electron dot symbols. They're really the same thing, but so I typically call them Lewis dot symbols, but again, sometimes people refer to them as electron dot symbols. So when atoms sort of interact with each other, really to form sort of a chemical bond, as we were talking about, I think yesterday as well. So if you think about, again, the sort of the structure of the atom and how it's sort of composed, we got sort of that central core that has the protons and neutrons. And out in that sort of empty space is that electrons, right, flying around randomly, as we talked about in this sort of electron cloud area. And really, as those sort of atoms come near each other or come close to each other, basically it's going to be those electrons, right, that basically interact with each other first, right? And that's really why bonding is pretty much based on just electrons. Electrons are pretty much the only things involved when we do chemical bonding. We don't do anything with protons. We don't do anything with neutrons. And that's also why when we have chemical bonding or say a chemical reaction and stuff like that, in a typical sort of chemical reaction, we pretty much have the maintenance of or the conservation of all the elements. Because we're not changing the protons. So as we talked about in the previous chapters, is the protons that basically determine the elements. So since obviously chemical bonding and that type of stuff involves only electrons, we obviously don't change any elements. So when they do come sort of in contact with each other, there really is only really one type of electrons that are really involved when we do bonding, and those are valence electrons. So valence electrons are the outermost electrons. They're the highest in energy. So if you remember, we were talking about sort of those valence electrons when we're talking about electron configuration. Those are our highest in energy. So your outermost. And that makes sense, right? Since they're the outermost. So, if you wrote your electron configuration, say 1s2, 2s2, 2p4, That would be for oxygen, which is 8. Now, when we look at oxygen, it has 2 electrons on the lower energy level. It has a grand total of 6 electrons on the second energy level. These would be the valence electrons here, right? 4 and 2 gives us 6 valence electrons. These guys down here would be the core electrons. And remember, you can sort of figure out basically the number of valence electrons by writing out the electron configuration. Probably don't want to do that all the time. So as we also talked about, you pretty much can't figure out the number of valence electrons because it does equal the group number, right? So it's equal to the group number. So again, if we looked at something like oxygen, oxygen's in group 6, and thus it has 6 valence electrons. So again, that's a much easier way to figure out the valence electrons, especially when you're doing bonding and stuff like that, rather than writing the electron configuration and trying to figure out, which ones are the valence electrons, which ones are the core electrons. So group number is their number of valence electrons. So everybody in group 1 has 1, 2, all the way across there. Now, when we draw these sort of symbols or Lewis dot symbols to help us sort of represent bonding, it basically consists of the symbol for the element and basically 1 dot for each of the valence electrons that are present. So if you have sort of your symbol, we use 1 dot. There's really no sort of technical rule other than we do not put more than basically 2 dots per side. So if you just think about it, kind of go around 1, 2, 3, 4, 5, 6, 7, and 8. So you basically could put 8 dots around it, as you may be familiar with. And bonding, 8 is a pretty good number there, an important number, and the maximum number that you can do when you do sort of a Lewis dot symbol. The X would represent the symbol, and again, a dot on each side. Like I said, there is no real technical rule. Most people kind of go clockwise with 1 dot and kind of pair them up afterwards. But again, it's usually as long as you kind of don't go 2 per side. I'm sorry, don't go more than 2 per side, which, you don't want to just keep putting dots on the top. Then it's okay in terms of your Lewis dot symbol, or again, electron dot symbol is sometimes referred to. So here's sort of a chart I made of Lewis dot symbols for everybody. And again, you can see here, everybody in group 1 has 1 valence electron. And again, these are all just the valence electrons that are being shown. 2 valence electrons in group 2, 3, 4, 5, 6, 7, and 8 all the way across. Remember that, we really only show valence electrons in our Lewis dot symbols. And remember that those are, again, the only ones that are involved in bonding. Obviously, these guys have more than just those electrons, like sodium, right? It has more than just 1 electron, but it has just 1 valence electron. And since that's the only one involved in bonding, that is why we only show those. You also notice that there's sort of a slight exception, which is helium here. And I don't know if it's such an exception, but obviously helium is part of group 8, but we do only see 2 electrons. And that's really because helium only has 2 electrons. So it obviously cannot have 8 electrons, because if you write the electron configuration for helium, it's 1s2, and that's it. It's pretty much so. Because helium only has 2 electrons, both of them are considered its valence electrons. And even though it's part of group 8, it cannot have 8 valence electrons because it only has basically 2 to begin with. Any questions on that so far? Okay. So we're going to talk now about, the different types of sort of bonding that we come across, and how these Lewis dot symbols can help us sort of understand them. So they can help us understand really the 2 different types of compounds and bonding that we typically come across. The first one is an ionic compound. And in an ionic compound or an ionic bond, which is obviously part of an ionic compound, pretty much it is between, as we will see, a metal and a non-metal. And basically what pretty much always happens in this case is the metal will basically give away its electrons. So you'll get the electrons that are transferred. And as these electrons are transferred, it is at that point, as we've talked about a little bit before, I think in the last chapter, it's at that point that obviously the metal loses electrons and then becomes positively charged in a cation. And that was a result of the metal. The nonmetal now picks up the electron or electrons and obviously now has an excess of electrons and has more electrons than protons and becomes negatively charged or an anion. And it is that attraction between the positive and negative charge that holds that together, and that's that electrostatic attraction. And as we'll talk about a number of times throughout this chapter and such, maybe we talked about before, it's also very important to remember that in this type of bonding, there is absolutely no sharing of electrons. So we have no sharing of electrons in an ionic compound or ionic bond. We have a complete transfer of electrons, usually from your metal to your non-metal in this case. And because we get this complete transfer of those electrons, it results in these guys really gaining full charges, if you will. So the metal gains a full positive charge, positive 2, positive 3, whatever many electrons it lost. And the non-metal really does gain a full negative charge or even more than one negative charge, depending on how many electrons that it sort of comes together. But a really major difference between an ionic compound and a covalent compound is just that. You have a transfer of electrons and you have absolutely no sharing of electrons between those two. So that's really sort of an important distinction between that and a covalent compound where, excuse me, in a covalent compound, it is also between actually two different things than what we see in an ionic compound. I guess I shouldn't say two different things, but is between actually two nonmetals. So when we talk about our covalent bond or covalent compounds, we're talking about really two nonmetals coming together. Now, when two nonmetals come together, what we end up getting is actually, in this case, sharing of electrons. So we do end up really getting sharing of electrons. So why do we see sort of, and we'll kind of see it as we go through this chapter, but why do we see sort of the difference in an ionic bond and a covalent bond? Why is there sort of a difference where one sort of transfers those electrons and one really sort of basically shares electrons? And it has a lot to do with all those periodic trends that we talked about yesterday. You just think about sort of the location on the periodic table of where we find everybody. And we got our nonmetals over here, right? And pretty much our metals over here. So when we put together in an ionic compound a metal and a nonmetal, they are on, for the most part, opposite sides of the periodic table, which means they basically will have opposite of those periodic trends. When we talked about our nonmetals, those are the guys that have all those trends that basically lead them to wanting to hang on to their electrons and also wanting to sort of gain more electrons, right? So all those sort of trends that went up and over to the right on the periodic table all led to the nonmetals either hanging on to their electrons or definitely wanting electrons. While all those trends, if you go on the opposite side to the left and down on the periodic table, all those trends led to the fact that those guys are pretty much, I don't really want to hang on to my electrons, you take them, and I'm not going to put up a big fight if you want to take my electrons. So we get, when we put together a metal and a non-metal, we end up getting a guy that is obviously willing to give up his electrons, which is the metal, and we have somebody that is willing to accept those electrons, which is a non-metal. And that's why in an ionic compound, we get that transfer of electrons, because the non-metal has the high ionization energy, high electron affinity, high electronegativity, is going to grab those electrons, while the metals have pretty much the opposite, low ionization energy, which means you can remove the electron easily, has low electron affinity, which means it's not willing to kind of hang on to its electrons, and low electronegativity, which means it has no interest in gaining electrons. So those two things really all sort of add up to what we do see when we put those things together, is that electron transfer happening. Opposite is true when we get to covalent bonding. When we get to covalent bonding, we're dealing with basically nonmetals and nonmetals, which are pretty much right next to each other on the periodic table, which means because they're next to each other on the periodic table, excuse me, they pretty much share almost similar of those periodic trends. They both have the willingness to kind of accept electrons. They both want to hang on to their electrons. So what you end up getting when you put together two nonmetals is a situation where you got two sort of elements going, I want to hang on to my electrons, and the other guy going, I want to hang on to my electrons, and they both go in pretty much, I want to kind of take some of your electrons as well. So the best that they could kind of work out is neither one of them is going to lay up or give up that electron and let it be transferred. They basically are going to sort of compromise, if you will, and there's going to be some type of sharing that's going to happen with those electrons. And that's sort of the best that they can sort of do in that situation. Now, as we'll talk about when we get into sort of covalent compounds and covalent bonds, that sharing may be kind of equal sharing, like they agree upon we're going to share everything equally, or it may be some unequal sharing. But there's some aspect of sharing that happens, again, because in this situation, we pretty much have two nonmetals that are pretty much located in the same spot on the periodic table, and pretty much will have very similar sort of properties. Any questions on that? Now, when we talk about that general rule, guys with low ionization energy, again, will tend to form cations. So again, remember, ionization energy is that energy that is required to remove an electron from the gas phase of an atom. So metals have low ionization energies, which means they can remove their electrons relatively easy. High negative electron affinity tend to form anions. Those are the guys that typically will, excuse me, will typically form anions, which are our nonmetals. Remember, electron affinity increases as we go up and to the right. All right, so the general rules that we're just sort of talking about, basically, as we just been discussing, basically that leads to the formation really of cations and from our metals, guys that typically will be giving off or releasing their electrons, while the other ones will basically be gaining electrons along the way, which are our nonmetals. So let's take a look at sort of ionic bonding and how we could use sort of these Lewis dot symbols to help us understand sort of what is happening in the formation of an ionic bond. So let's take a look at lithium. Let's take a look at lithium fluoride. So lithium has an electron configuration of 1s2, 2s1. Fluorine has a configuration of 1s2, 2s2, 2p5. All right, so looking at lithium fluoride, we have 1s2, 2s1. Again here, the 2s1 here in the second energy level going to give us our one valence electron for our lithium. Also remember that lithium is group number 1 on the periodic table, which means it has 1 valence electron. When we look at fluorine, it has these guys here in the second energy level, and that would be 7 valence electrons, which would be group number 7 on the periodic table. So if we were to basically draw our Lewis dot symbols for each of these guys, we have our lithium here, which has its 1 dot for its 1 valence electron. We have our fluorine with its 1 dot for its 1 valence electron. And essentially what's going to happen is our lithium is going to basically transfer its electron over. And when it does so, we're going to make this ionic compound that's over here, lithium fluoride. And what happens is, just to sort of clarify, the lithium now has lost its 1 electron and becomes positively charged. The fluorine has picked up that electron and now becomes negatively charged, and we get this ionic compound. Now, it's really important when you draw these things for ionic compounds is that we do indicate the charges, as we see here. And these charges indicate that we are not sharing electrons. So there's absolutely no sharing of electrons. This is an ionic compound, and we have a positive and negative charge. And that's really what's holding this guy together. So it's really important to include those in your drawings. Otherwise, without it, it's implying that there's some sharing of electrons. Also, sometimes people will put brackets around it, at least one of them. Sometimes people will put brackets around both of the ions that are formed here. We form a cation and an anion in this particular case. But some way to sort of distinguish that, there's really no sharing of electrons that are happening here. But we do have sort of that transfer of electrons. So what happened really when we look at lithium and fluoride here in terms of its electron configuration sort of before and after? So lithium over here was 1s2, 2s1. Fluorine was 1s2, 2s2, and 2p5 in this particular case. It is lithium that gave away this electron over there, actually over here to the p. And when it does, the lithium now with the +1 charge ends up with a configuration of a 1s2 as it lost its electron. The fluorine, which picked up the electron and put it right there in the p orbitals, ends up with 1s2, 2s2, 2p6. Who are these configurations? Well, 1s2 is 2 electrons. That is the same configuration as helium. 1s2, 2s2, 2p6 is 10 electrons, which is the same configuration as neon. And this is an important concept here in terms of ionic bonding, is by transferring electrons in this particular case, it allowed both lithium and fluorine to both reach noble gas configuration. So we have helium and neon's configuration for both of them. And remember, as I mentioned a number of times, that is basically the ultimate goal of any type of bonding. The ultimate goal of any type of bonding is basically we want to get to noble gas configuration, have the exact same electron configuration really as a noble gas, because they are very, very stable. So in the case of lithium and fluorine, they're able to do that by losing electrons and gaining electrons to reach that noble gas configuration. Any questions on that there? So obviously what holds that together, as we've been talking about since this is an ionic bond, is the attraction between the positively charged lithium, in this case, and the negatively charged fluorine, and that positive negative attraction between the two. This is basically what represents a ionic bond. As we talked about previously and just a second ago, the purpose of this is what we see is when our metals lose electrons, and become positively charged, they back up to the previous noble gas. So if you think about lithium, the previous noble gas to it was helium. When our nonmetals gain electrons, they go forward to the next noble gas. So if you think about fluorine, look on the periodic table, the next noble gas that comes after it is neon in this particular case. Any questions on that there? All right, so let's take a look at another one here. Let's take a look at calcium oxide. Calcium oxide. Calcium oxide is obviously between calcium and oxygen. So if we think about our two guys here, we have calcium, which is group number 2 on the periodic table. So it will have 2 valence electrons. We also have oxygen, which will have 6 valence electrons. So what's going to happen in this particular case is our calcium will basically give up some electrons. So it will give up an electron here. But let's think about what happens with calcium. Let's kind of think about the periodic table, if you will. We got calcium here. We have potassium here. And then the next noble gas that kind of goes before it is argon. So if calcium just lays up 1 electron, it really only moves it back to potassium sort of configuration. So because it has 2 electrons, it's able to sort of give away both electrons. And now that's going to kind of move them back into argon's configuration. When it does so, again, we get calcium that now has lost 2 electrons, has a positive 2 charge. The oxygen gained those 2 electrons, giving it a negative 2 charge. And again, we get this ionic compound that is basically formed. What happens in terms of our configuration? Well, calcium started out as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Oxygen started out as 1s2, 2s2, 2p4. The calcium gave away these 2 electrons, which leaves the calcium over here as 1s2, 2s2, 2p6, 3s2, 3p6. And if you add all that up, that is 6 and 2 and 2 is 10 and 18 basically. And that means that calcium here has achieved, as I showed up here, argon's configuration. Oxygen gaining 2 electrons are going to end up there. When it does 1s2, 2s2, 2p6, that is 10 electrons, which again is the same configuration as neon. So both of these guys, argon, calcium, by giving away both electrons, able to achieve the noble gas configuration of argon. Oxygen, by accepting those 2 electrons, able to achieve the noble gas configuration of neon. Again, the purpose of bonding is for everybody to get to that sort of group 8 situation and that noble gas situation. Questions on that there? All right, let's take a look at another sort of situation, actually using the 2 elements that we just used, and we'll put the other 2 together. What happens if we take calcium and we put it together with fluorine like we had before? All right, so well, calcium here is the same configuration as we saw up there. That is basically argon 4s2, the 4s2, the 2 there are the 2 electrons, and our fluorine, which is our 1s2, 2s2, 2p5. And in this situation, our calcium is going to give up its electron like we saw previously. Now, we run into a little situation at this point, and the situation that we run into is our fluorine is going to pick up that electron here. It is now full. It's got really no more room for any more electrons. And that's problematic for calcium because calcium has now only given away one electron, which now moves it to potassium's configuration. And potassium is really not a noble gas configuration. It's an alkali metal configuration. And it's not really what calcium wants to do. Calcium wants to give away 2 electrons so it could end up at argon. And it can't do it, obviously, in this case of fluorine, because this fluorine is full. So what is needed in this case is actually not one fluorine, but we actually need one more fluorine. And we need one more fluorine because that will allow calcium now a place to offload its second electron and allow it now to jump to argon's configuration in this particular case. So in this particular case, what ends up happening is we end up with a calcium that has now lost 2 electrons, 1 to each fluorine. And we end up with one fluorine that picked up 1 electron. And we ended up with another fluorine that picked up 1 electron. And what we end up now with is calcium that has lost 2 electrons. So as we saw above, that allows calcium to achieve noble gas configuration of argon. And each of the fluorines basically picked up an electron, which gets each of the fluorines here to the same configuration as neon. So in this case, all 3 of these guys, by gaining and losing electrons, are able to achieve noble gas configuration. And that is why, as you may be familiar with, when we put together a cation with an anion, we always put it together in the simplest way to get to a 0 charge. And that's why the formula for something like calcium fluoride is CaF2. Because without the extra fluorine there, calcium could not reach noble gas configuration. And that's essentially the reason behind when you learned about probably nomenclature, ionic compounds, that positive and negative guys, you put it together to equal 0. The purpose of doing that is to allow everybody in an ionic compound basically to reach that noble gas configuration. Any questions on that there? Any questions on ionic bonding? So this is representing ionic bonding, and we want to show the electrons being transferred, and you definitely want to show the charges when you're all said and done on your ionic compound. Any questions on that? In a proper ionic bond or ionic compound, really the charges balance each other out to 0. And the reason for that is, again, it allows everybody to reach noble gas configuration. All right, then we're going to switch gears here and now talk about covalent bonding. And again, covalent bonding is a little bit different than the ionic bonding that we were talking about just a second ago. We're now talking about 2 nonmetals together, and we're talking about sharing of electrons here. And again, as we talked about before, the major difference between the 2 is now we're talking about, on the periodic table, 2 guys coming together pretty much in the same location on the periodic table, which again means that they are going to share pretty much similar periodic trends, which means they both want to pretty much hang on to their electrons. And I'm sorry here, the dots are all out of place here, so I'm just going to cross that out. We'll redraw that. All right, so Gilbert Lewis, which is why they're called Lewis structures, Lewis dot symbols. He developed the concept of chemical bonding as really sharing of electrons. So if we take something like hydrogen, which has one valence electron, and we put it together basically with another hydrogen that has one valence electron, they will basically come together, and because they're both hydrogen for sure in this case, they are both going to have identical periodic trends or properties. So basically they're going to want those electrons the same, and they're going to end up sharing those electrons, which we could represent by two dots such as this. We could also represent this covalent bond with a line. A line represents two electrons that are being shared between two atoms. And when we talk about these electrons, again, they are being shared between these two. So the two in the middle count for the hydrogen there on the left. The two in the middle count for the hydrogen on the right. And we got this area between them where we do get this sharing of electrons, which is again an covalent bond in this particular case. Oops. And as I mentioned before, you could either use the dots or the lines to represent that, a bonding pair of electrons such as that. So in this particular case, both hydrogens pretty much ends up with two electrons. So you may be saying, well, two electrons isn't like 8 the important number. But for hydrogen, if you look at the periodic table, that's hydrogen, that is helium, and that is number 1, and that is number 2. Hydrogen only really needs and should only get to 2 electrons because that moves it really forward to helium's configuration. Helium is a noble gas, so hydrogen is perfectly fine with that. It should never have more than 2, basically. Hydrogen should always just make 1 bond, 2 electrons, because that will allow it to reach noble gas configuration. So that's a really important thing to remember when we talk about hydrogen, especially covalent bonding. People have a tendency to want to like triple bond hydrogen and put dots all the way around hydrogen, but really hydrogen just needs 2 electrons. And again, the reason for that is it allows it to get to helium's configuration, which is right next door. So in a covalent bond, unlike a ionic bond where we have a transfer of electrons, we end up getting a sharing of electrons that occur. And basically what's sort of happening, in a very bad drawing here, let's try this out. You know, we got the 2 sort of electrons there that are being shared. Remember, there is a nucleus, right, in both of these guys. And these guys are negatively charged, and those are electrons. So these electrons are attracted to like the nucleus over here, but they're also sort of attracted to the nucleus over there. And basically that attraction to both nucleuses sort of locks everybody into place and really makes that bond. So obviously nothing changes along the way. Now, if we look at F2 and we look at the electron configuration for fluorine, 1s2, 2s2, 2p5, and we're doing 2 fluorines. They're both group 7. And these are the 7 valence electrons here, 5 and 2. And basically what's going to happen again, because they're both nonmetals, they're both identical to each other. This fluorine on the right, this fluorine on the left is going to go, I would like it. And the other one would go, I would like it as well. And they're just going to compromise on, we'll just try to share them between them. So we're going to share these electrons. So what happens when they share these electrons is the 2 in the middle does count for the guy on the left. The 2 in the middle counts for the guy on the right-hand side here. And when we count up the electrons for the guy on the left, 2, 4, 6, 8. When we count up for the electrons on the right, 2, 4, 6, 8. Now, by sharing electrons here, rather than transferring electrons, both of these guys pretty much hit 8 valence electrons, which puts them in the same realm as group 8 on the periodic table in the noble gases. And they achieve that sort of noble gas configuration here by sharing electrons to do that. You could obviously represent this with a line for the electrons that are being shared. When we look at it there, again, either way there is an acceptable way to represent this bonding. This again would be covalent bonding, sharing of electrons that are happening here. When we look at this, there are some different types of electrons that we do see in our picture here, our Lewis structure. Now, all of the dots that are sort of on the outside here, bad circle. All these guys here represent which are known as lone pairs. They're not involved in bonding. They're also more commonly these days called non-bonding electrons. I'm older, so I call it lone pairs a lot, but lone pairs or non-bonding electrons are really the same thing. And again, most books and stuff call it non-bonding electrons now. But non-bonding electrons are obviously, much like the name implies, there are electrons that are not involved in a bond. There's no other element on the other side of those sort of electrons. They are there and they're not involved in the bond. Now, the ones that are involved in the bond does have a very creative name, and that would be these guys right here. These are what are referred to as bonding electrons, and it's a very creative name. So bonding electrons, much like the name implies, are electrons that are obviously making a bond. Non-bonding electrons are really the dots. When you draw these things, these sort of Lewis structures, you should always include all of those electrons in your pictures. Both the non-bonding electrons and the bonding electrons should be really shown in your pictures. Again, the non-bonding electrons are shown as dots, and you do have sort of a choice for the bonding electrons. You could also show those as dots, or you could show them as lines as we see here. Any questions on that there? So a Lewis structure really is a representation of bonding and again, sharing of electrons happening here in covalent bonding when we have our two nonmetals basically come together. If we look at something like water, for example, water, for example, is H2O, obviously, and if we draw it, we do see that the hydrogen on each side, by sharing electrons there with the oxygen, they both again are able to achieve those 2 electrons, which, as we talked about, allows hydrogen really to get to helium and be happy. Now, the oxygen, as we can see on the bottom, by sharing with actually both of the hydrogens, is able to achieve 8 electrons around it, which again allows it to reach basically that noble gas configuration. And that's the same thing that we see there with the fluorine, where we see, again, both fluorines also able to achieve 8 valence electrons and actually reach that sort of noble gas configuration, or that group 8. So obviously that brings us to a really important sort of rule here, and that is the Octet Rule. And when we're doing bonding, the Octet Rule basically states that pretty much everybody is going to continue to make bonds to reach 8 valence electrons around them. Again, that's going to allow anybody in a covalent situation to basically move themselves to the same electron configuration as group 8. Again, by sharing electrons here, because they're not going to be willing to give up their electrons, they are going to share them between the two nonmetals. The exception is, as we've talked about, hydrogen. Because hydrogen is pretty much right before helium, it only needs to get to 2. So again, when you draw hydrogen, it pretty much should always look like this. Hydrogen should also always be on the outside. Shouldn't have the circle, by the way, but hydrogen should always be on the outside. It should never be in the center of a picture because it'll have more than 2 electrons, but it should always look like that. There should never be any type of double bonding happening, triple bonding happening, single bonds with dots all the way around. These are all incorrect. Because that is too many electrons for hydrogen. That is sometimes referred to as a duet rule, basically allowing hydrogen again to reach that helium configuration and be pretty much happy. Any questions on that there? Now, there are sometimes situations where we have multiple types of bonds. We could have a single bond, which is basically one bond, double bond, or a triple bond. So in a single bond, as we saw here with fluorine, we basically are sharing basically one pair of electrons being shared. Again, can be represented by the dots, can be represented by a single line between them. When we get to a double bond, what we end up with is, as we can see here, between the carbon and the oxygen, 2 pairs of electrons, or again, that is a total of 4 electrons being shared, or could be represented by a double line. So a single bond, 1 pair of electrons represented by a line. Double bond, 4 total electrons, or 2 pairs of electrons, are represented obviously by a double bond. And obviously we can have a triple bond situation where again we are sharing 3 pairs of electrons, as we see here in the nitrogen, basically 3 pairs of electrons being shared. Or that's a total of 6 total electrons, again represented by 6 dots, or 1, 2, and 3 lines. So try that again. 1, 2, 3 lines. There we go. Why do we do double bonds? Why do we do triple bonds? Or why does that sort of occur? And it really occurs for the same basic sort of reason. It occurs for what we see here. In certain situations, a single bond by itself is not going to allow everybody to get to 8 electrons. So sometimes the only way for everybody to sort of get to that 8 electrons, be able to get to the noble gas configuration, is to make multiple bonds. Sometimes it requires a double bond and you're good. Maybe it requires 2 double bonds, like what we see here in carbon dioxide. In order for carbon to really reach 8 electrons, it actually needs to do 2 double bonds in that case to allow it to get to that 8 electrons. Sometimes, again, double bonds is not going to be sufficient enough, and you do need a triple bond to allow everybody to get to 8 electrons. But the goal here is, again, to get to 8 electrons, and again, sometimes you do need to double bond or triple bond. A reminder, and as we'll talk about it when we do get to sort of drawing some of these guys, it's not usually a great idea to double bond or triple bond sort of out of the box. We oftentimes save double bonds or triple bonds to sort of fix situations where we're not getting to the octet rule. So sometimes that's sort of the way we want to do that. Again, sometimes people have a notion they just want to kind of double bond, triple bond right out of the box where they're drawing these things. And it doesn't always lead to perhaps the best structure, and sometimes it will lead to really an incorrect structure. So it's usually good to sort of think about in your head that, I really maybe want to kind of double bond or triple bond in a situation where I'm trying to get everybody to 8 to sort of fix a situation where maybe somebody did not get to 8 valence electrons. We'll obviously talk about the steps to drawing Lewis structures in just a second, but that's a good thing to kind of keep in mind. But next, we're going to talk about really sharing of electrons. And again, this is a really applied, truthfully, I mean, you can really apply it to ionic compounds as well, but basically we use electronegativity a lot of times to help us understand the sharing that's happening. In covalent compounds or covalent bonds. We could also, again, use it for ionic bonds. But the deal is with ionic bonds, as we'll talk about here, you really don't necessarily need it, because if you could recognize something as a metal or a non-metal, you know there's going to be a transfer of electrons. So you don't really need to look at the electronegativity to tell you that, but it can tell you that as well. But we're going to look at electronegativity, and remember, electronegativity is that ability, as we talked about, of an atom to bring electrons towards itself. And remember, as we talked about the trend, when we look at the periodic table, it increases as we go this way. And again, as we talk about, as we will see here in a second, fluorine being the most electronegative, and it decreases as we go down. So electronegativity is really a very key component into understanding, how fairly, for example, will those electrons sort of be shared between two different elements. And it does help us sort of distinguish between covalent compounds and ionic compounds, as we will see in a second as well, and as we maybe talked a little bit about the other day. There's a very big difference between the electronegativity in terms of metals and non-metals, which again is why we get that transfer of electrons, and not as big of a difference in electronegativity between non-metals and non-metals, which is why we see sort of sharing of electrons occurring. So if we look at something like H2, we would expect that those electrons basically within that bond that are being shared by those two hydrogens to be shared pretty equally. And that's because basically we're looking at a hydrogen on one side that's kind of pulling those electrons, but we have almost the identical hydrogen, or pretty much an identical hydrogen on the other side pulling. So if you think about it sort of like a rope, they're both kind of pulling on the rope pretty equally. The rope is probably not going to go very much or move very much. And the same thing with those electrons. They're going to be sort of bound to each of those guys pretty equally and shared equally. And when we do get that sort of equal sharing of electrons, that is what is referred to as a nonpolar covalent bond. So when we have equal sharing of electrons, that is what is referred to as a nonpolar covalent bond. Most people just straight up call it a nonpolar bond. It's implied to be covalent, but it is a nonpolar covalent bond. It's also the same thing that we see when we look at fluorine, right? Again, those electrons that are in the middle would be hanging out by this fluorine, and electrons on the middle would be hanging out on this fluorine pretty equally, and we would expect equal sharing basically of the electrons, between the two fluorines in this particular case. So we get that sort of equal sharing of electrons, and we get what is referred to as a nonpolar bond. But what happens if we're not really dealing with two elements that are the same? Would we still expect sort of the electrons to be shared equally? So what happens if we take one of each of those guys, we take a hydrogen and a fluorine and put it together, would those electrons still be shared equally? And the answer is no, they really wouldn't in this case. So when we take our hydrogen and our fluorine here, again, The hydrogen gets those 2 electrons in the middle. The fluorine also gets those 2 electrons in the middle. The difference, though, is if you remember just in general, like we've been talking about, that the electronegativity value of fluorine is pretty much the most of anybody, which means when some other element hooks up with fluorine, fluorine's going to go, well, I kind of want the electrons. So fluorine's going to kind of hog all the electrons and get a lot of the electrons to come and kind of hang out over by fluorine. A little bit of them will hang out, by the hydrogen here. And we then get really this unequal sharing of these electrons occurring. Because basically, if you kind of go back to like the rope and like a tug of war sort of situation, on one side, in this case, you got somebody that's really, really strong. On the other side, you got somebody that's kind of weak. And obviously, the guy pulling on the rope on the strong side is going to probably make the guy on the other side kind of move, and you'll see the rope move as well. And again, the electrons are going to be moving towards the fluorine in this case because it's going to be pulling those electrons towards itself a lot more than the hydrogen will. In a tug of war situation, even the person that's really small getting pulled with the rope, they typically hang on to the rope, right, until they hit the mud pile. So they hang on to the rope even though they're being pulled. Same idea here, even though the fluorine is really pulling those electrons to its side, the hydrogen's like hanging on to the rope until he hits the mud pile. And he's not going to let go of the rope or the electrons completely. There is going to be some aspect of sharing, but it is definitely some unequal sharing that's occurring here. What is the consequence of this sort of unequal sharing that occurs between, say, the hydrogen and the fluorine? Well, part of the consequence is, even though they are still, again, sharing those electrons unequally towards the fluorine, because the electrons are hanging out on the fluorine side more than they're hanging out on the hydrogen side, it creates what is known as a partially negative charge on the fluorine. That's a delta symbol, delta negative, partially negative charge on the fluorine. And on the hydrogen, because the electrons are all kind of hanging out at the fluorine side, the hydrogen now is sort of electron deficient and is a little bit more positive and creates a partially positive charge there on the hydrogen side. This could also be represented a lot of times with an arrow, where the arrow is pointing to the side that is more negative, more electronegative. And the back part of the arrow, which kind of makes like a plus sign, is to the part that's more positive in that bond, or least electronegative. And what this represents is a polar covalent bond, really unequal sharing of electrons here. Or again, much like a nonpolar bond, instead of people saying nonpolar covalent bond, most of the time people say nonpolar bond, and here most of the time people will just call it a polar bond rather than a polar covalent bond. So here we end up with that unequal sharing of electrons, and overall what's going to cause is a side to that bond that is more positive and a side to that bond that is more negative. And you do not get that in a nonpolar bond, because in a nonpolar bond, you pretty much have that equal sharing of electrons, which means there's really no side that is more positive or more negative in that type of bond. But here in a polar bond, you do get a side that is, again, more positive and more negative. Again, if this sort of smear here is the electron density, greater amount of electron density over here on there to fluorine, making this side more negative, less kind of electron density near the hydrogen, making this side more positive. And in this type of polar bond, we do get this sort of charges to sort of develop. Why are they called partially positive charges and partially negative charges. So on the other page, I drew that. And again, that's a way you could represent that as partially positive and partially negative. They are partially positive, partially negatively charged because there is still some aspect of sharing happening here. They have not been completely transferred where they both gain a complete positive charge and a complete negative charge. So because kind of like, again, the tug of war example, the little guy that's being pulled is still hanging onto the rope, even though he's really, barely hanging on, and he's getting moved and stuff like that. But because he's still hanging onto it, kind of like in this situation, you can think of the hydrogen as, almost giving it up, but still hanging on to it. And there's still some aspect of sharing where it could be very unequal, which it is in this case, very, very unequal in terms of the sharing, almost to the point where there's going to be a transfer of electrons, but there really isn't, because again, he's still barely hanging on to his electrons as well. Any questions on that? So again, we get that partially negative charge where we have the delta symbol to represent that. So really, when we think about the different types of bondings, there's sort of three types of bondings and sort of the differences that we see here. Yeah, to answer your question about the arrows, I'll say yes and no. So in general, the question is, do you have to draw the arrows to indicate the difference in electronegativity? So probably 9 times out of 10, the answer is no, you won't have to draw those arrows if you're just asked to draw the Lewis structure. There are some times when you are asked to draw those areas or show, as we'll talk about here coming up, that's really what is sometimes referred to as bond polarity. And sometimes you're asked to indicate the bond polarity. And the one way that you can kind of indicate that is to draw those arrows. So the answer is like kind of no in general. And in most cases, you wouldn't have to draw the sort of arrows, nor would you have to sort of draw the partially positive, partially negative charges, and probably a normal question. But there are certain questions and certain times where you will have to sort of indicate those arrows to indicate sort of the bond polarity, if it's a polar bond or not. So probably most times you won't, but there are some times where you may have to draw them. But you definitely don't have to do it every single time that you draw a Lewis structure, for sure. Other questions on that? So to sort of summarize the sort of 3 types of bonding that we talked about, you could kind of think of them as sort of 2 extremes with sort of one in the middle. So what I mean by that is kind of like on one extreme, you have really an ionic bond. And an ionic bond, as we've been talking about, is definitely between a metal and a non-metal. And always what's going to happen in this situation, as we've been talking about, is the metal is going to give us our transfer of electrons. Resulting is, as we talked about, a cation, which is positively charged, and an anion, which is negatively charged. And in this situation with an ionic bond, as we've been talking about, because we are actually getting a complete transfer of those electrons, we do end up with 2 things that actually do have sort of full charges, if you will, full positive charges, full negative charges, are cation and anion. And as we talked about, it is that attraction between those 2 that holds that together, but we have absolutely no sharing of electrons. And an example of that would obviously be something like sodium chloride, right? Sodium is a metal, chlorine is a non-metal. Now, once you sort of see this combination, once you can sort of completely identify, oh, I'm dealing with a metal and a non-metal, you really don't need any other information. We'll talk about electronegativity here a little bit more in just a second, but you really don't need any other information to make a pretty educated guess that you're dealing with an ionic bond, you're dealing with a transfer of electrons. On the other end of the extreme, we have sort of a non-polar covalent bond. And in a non-polar covalent bond, this is, again, different things involved. Two nonmetals. We have absolutely equal sharing of electrons. So everybody's happy. Everybody's equally sharing those electrons. Again, to that tug of war sort of thing. They're pulling on the rope exactly the same. Nobody's pulling more than somebody else. And we get this really, really kind of like almost a neutral sort of bond. There's really no difference in charge on one side or the other. Some examples of this is hydrogen and fluorine that we talked about. So at one end, we got this complete transfer of electrons. On the other end, we got this complete perfect sharing of electrons. And sort of in the middle, you could think of a polar covalent bond, or just a polar bond, which is also between two nonmetals. And we have unequal sharing of electrons. And an example here would obviously be HF, which we see there to the left. Again, the fluorine being more electronegative, pulling those electrons, the hydrogen becoming more positive in that sort of bond because it's kind of losing its electrons, but hasn't completely lost it. So again, that's sort of the three situations of bonding that we come across. One situation on the far right there, nonpolar bond, perfect sharing of electrons. In the middle, we have a polar bond. We have sharing of electrons, but unequal sharing of electrons. So definitely not equal sharing, but not such unequal sharing of electrons that we actually see the electrons being transferred, just really sometimes very unequal sharing, but somebody's still hanging on. Both guys are still hanging on in terms of the electrons. And then we go all the way to the other side where we have the ionic bond, where we do see it's such unequal sort of situation in terms of electronegativity and other factors that we actually do see a complete transfer of one electron, two electrons, however many electrons from one to the next, creating that ionic bond. Any questions on the differences between those three types of bonding? And sometimes, I personally call it a nonpolar bond, and most people will call it a nonpolar bond. But if you have sort of perfect equal sharing of electrons, like in the case, as we'll talk about here in just a second, between, say, hydrogen and hydrogen or fluorine and fluorine, sometimes that nonpolar bond is covalent bond is sometimes referred to as a pure covalent bond when you have like it's absolutely perfect equal sharing of those electrons. And that obviously would occur in H2 because they're both hydrogen, which means they are perfectly going to pull the same on each side of those electrons. Same thing with fluorine. They're going to pull equally the same on both of those electrons. So sometimes you'll hear the term used, and I won't use it probably too much, but maybe in books and stuff like that. You'll sometimes hear the term pure covalent bond. And when you hear pure covalent bond, it really is talking about a nonpolar bond. It's basically just saying that is like the perfect situation in terms of sharing. They are perfectly equal sharing those electrons, pretty much 100% equal with each other. So you may be asking yourself, like, how do I know, who's doing what in terms of the sharing of electrons? How do I know if the electrons are going to be shared, really equally or unequally? And really the major thing that we look at in most cases in terms of bonding and trying to determine sort of, how those electrons are going to be actually shared is actually electronegativity. So obviously we've talked about electronegativity in terms of what it is and sort of what is happening. But electronegativity, again, is really what helps us distinguish between a nonpolar bond and a polar bond. We can also use it to distinguish between an ionic bond as well. But as I mentioned before, as will become probably pretty obvious to you here in just a second, you really don't need electronegativity sort of values and stuff like that to help you determine if you're dealing with an ionic bond. Really all you need is that's a metal and that's a non-metal, that's an ionic bond is pretty much what you need. So you don't really actually need necessarily the electronegativity values to help you determine if you're dealing with an ionic bond. You definitely can, but a lot of times we really do sort of use electronegativity more to look at covalent bonds, sharing of electrons. And when we do, what we're looking at is specifically between these two elements, how those electrons are going to be shared between those two elements. Again, electronegativity, as we've talked about, is the ability of that atom basically to attract electrons to itself. As we talked about, the general trend is up and to the right is more electronegative. And again, fluorine is the most electronegative element we could have. And again, down and to the left on the periodic table is the least or decreasing electronegativity. The electronegativity of an element is based on electron affinity and ionization energy. Remember, electron affinity is the energy change that occurs when somebody gains an electron, and the ionization energy is the energy required to remove an electron. So again, as we talked about, I think in the last chapter, we associate this with like things becoming more negative and this guy with things becoming more positive. And remember, again, in terms of location, high electron affinity here, right? High electron affinity and also high ionization energy in this part of the periodic table, as opposed to in this part of the periodic table, right? We have low electron affinity and a low ionization energy. Again, as we talked about, those factors basically mean these guys are willing to give up those electrons. The high electron affinity on the upper right and high ionization energy means that these guys are not willing to give up their electrons all that much. So that's what we see also in the pattern of electronegativity. We see it increasing this way and decreasing this way in terms of electronegativity. So it does follow very nicely. Again, all of those sort of periodic trends that we've been talking about in that last chapter. And that's why we see fluorine, which is the highest in electronegativity. It has a very high electron affinity and a high ionization energy, which means it's not going to lay up its electrons. It's basically going to want to go on to accept electrons rather than give them away. As opposed to if we go to sodium, which again is on the left-hand side of the periodic table, it has a lower electron affinity and a lower ionization energy and is willing to give up its electrons without a big sort of struggle, if you will. So how do we determine, whether or not this bond is going to be a polar bond, a non-polar bond, or even an ionic bond? Is Linus Pauling basically came up with a method of assigning electronegativity values to most elements. And we could use what is sometimes referred to as the difference in electronegativity. So the difference in electronegativity to help us determine, are we going to be dealing with, again, that sort of polar bond, non-polar bond, or ionic bond. He assigned values of 0 to 4 in terms of electronegativity values. 4 is the most electronegative, and 0 being not so much, right? So no electronegativity. So these are sort of the values that he assigned to each of those elements, and it does fit with, again, that general trend that we've been talking about, that as you go up on the periodic table and over, more electronegative. As you go down and to the left there, least electronegative. So let's take a look at a table, and this is a similar table. You have one in your book that's similar to this one, but this one basically shows us all the electronegativity values that we see. We see over here on the right, fluorine has a value of 4 up and to the right, the farthest you could go. And we see our highest value of 4. As we go to the left and over here, far left, we're approaching 0. So a very big difference in electronegativity between them, the left-hand side of the periodic table and the right-hand side of the periodic table. You may be wondering, there is the noble gases, right, that are sort of next to fluorine and all those guys. Noble gases are chemically inert. They are stable. They are, as we've been talking about, pretty much what everybody is aiming to achieve. So they pretty much are not reactive, and they have 0 in terms of electronegativity values. They're perfectly fine the way they are. That's why you don't see them on the table. That's why we see it end with fluorine, because again, all these guys will do some type of bonding, either covalent bonding, ionic bonding, in an effort to get over here to group 8, where they're hanging out. So again, they pretty much are never on this table because they're not very reactive at all. So how do we do that? We take the change in electronegativity. So the change in electronegativity value. And if you calculate the change in electronegativity value, and it is somewhere between 0 to 0.4 difference, the way that we calculate the change in electronegativity value is we simply subtract the two numbers. So the two numbers that are involved in the bond, that we go to the table, we find their two electronegativity values, and we subtract them. And if you do that and you get a number between 0 and 0.4, it's considered a nonpolar bond. Now, if you kind of go above 0.4, we'll call it 0.5, I guess, really above 0.4 to below 2, that is what is usually considered a polar bond. And usually if you find yourself with a difference of above 2, not 100% of the time is it perfect. That is an ionic bond. Again, you really don't have to worry about ionic bonds, because if you can recognize it as a metal, non-metal, it's an ionic bond. Doesn't work 100% of the time, but approximately above 2 will give you that sort of ionic bond. So let's take a look at the few examples that we just talked about there with the 3 types of bonding, right? So we had on one end of the extreme, if you remember in that example, we had our friend sodium chloride. In the middle, we had HF, and on the other end of the extreme, right, where we had our nonpolar bond, we had H2, F2. We'll just do H2. All right, so let's take a look at our electronegativity values here. So hydrogen, if we go to the chart there, is 2.1. So if we did the change in electronegativity for H2, it would be 2.1 minus 2.1. That is an electronegativity difference of 0, which definitely puts us in a nonpolar bond, which is why this is a nonpolar bond. Now, as I mentioned earlier, when I was talking about sometimes people will refer to this as a pure covalent bond, because that is like a 0 difference in electronegativity values. That is a perfect sharing of electrons. So sometimes people will call this a pure covalent bond. And again, a pure covalent bond is a pretty much nonpolar bond. I personally, again, will go with nonpolar bond here for that. But again, you'll see that sometimes with that perfect sharing of electrons. What happens when we get to HF? Well, H, again, from the table is 2.1 in terms of its value. Fluorine from the table is a value of 4, which means when we do the difference in electronegativity values, we take 4 minus 2.1. That's a lot of math there. That is going to be like a 1.9, I hope. And a difference of 1.9, if we go to our table, puts us here. Not quite 2, but pretty darn close, right? But we're still below 2, and this would be classified, obviously, as a polar bond, as we've been talking about. And it also gives us a feeling of how unequal that sharing is. Really, in this case, as you can see, it's almost to the point of ionic, where we get a transfer of electrons. And it basically means that hydrogen is kind of like barely hanging on there, but it's still hanging on. And almost all of the electrons are hanging out near the fluorine side because of that big difference in electronegativity. If we look at sodium, which is 0.9, And we look at chlorine, which is over there at 3. And we do our difference in electronegativity here of 3 minus 0.9. That is going to give us a 2.1 difference. That is definitely above 2, which means we would expect this to be an ionic bond. Again, you really, and this is what I've been talking about, you really don't even need these values. You can simply look at this and go, that's a metal, that's a non-metal, it's going to be ionic, and you would be probably safe almost all of the time. Any questions on that there? So why don't you try some here? Why don't you figure out the difference in electronegativity for these bonds and determine, is it polar, non-polar, or ionic? Why don't you do, let's do the carbon-oxygen bond. Let's do carbon-hydrogen bond. Let's do oxygen, sulfur. Let's do carbon sulfur here. All right, so for each of these, use the table, determine the difference in electronegativity, and determine whether it's nonpolar, polar, or ionic in this particular case. So there's a question while you're doing that. There's a question about, what would happen if you had like a metal and a non-metal, and you did the difference in electronegativity, and it wasn't above 2. And the answer is the above 2 is just a sort of a general cutoff. It's not perfect, and that's why I say if you're looking at ionic bonds, as long as you can recognize it as a metal and non-metal, it's an ionic bond. It's not going to be perfect. There's several combinations where if you take a metal and a non-metal, you will end up with maybe a little less than 2. 2 is just sort of I won't say a generic cutoff, but a relative cutoff, and it's not 100% of the time always going to be above 2. But as long as you can recognize it as a metal and a non-metal, you should be able to recognize it as being ionic. Okay, let's take a look here and see how we're doing since we're getting to the end. So the carbon-oxygen one first. So carbon up there is 2.5. Oxygen is 3.5. So again, we take the change in electronegativity, going to be 3.5 minus 2.5. That is going to give us a difference of 1, which does put us in this range. And this is going to be a polar bond. Any questions on that one there? Looking at carbon and hydrogen, carbon is 2.5, hydrogen is 2.1. Thus, our difference in electronegativity here going to be 2.5 minus 2.1 there. That's going to be 0.4. That 0.4 is the sort of boundary, if you will, for nonpolar, and this would be considered a nonpolar bond. And the reason it is nonpolar is really that carbon-hydrogen bond is the basis of organic chemistry. Organic molecules are nonpolar, so that's really why the cutoff's at 0.4 is really for this bond right here. This carbon-hydrogen bond is a nonpolar bond. Now, this nonpolar bond versus this nonpolar bond, there is a slight difference, right? In the case of H2, we have actually equal sharing of electrons, right? In the case of carbon and hydrogen, it is still considered equal sharing of electrons, but in reality, the electrons would just slightly be moving towards the carbon, right? So it's not really 100% perfect equal sharing of electrons, but it's enough equal sharing of electrons to be considered overall equal sharing of electrons in a nonpolar bond. And that's why there is that slight distinction that sometimes you will see people use, like we talked about just a second ago, that in this case, this is sometimes also referred to as a pure covalent bond because we got that absolute perfect equal sharing of electrons. They're both considered nonpolar bonds, but one is sort of like a perfect sharing. The other one is considered semi-perfect and still considered equal sharing. But there is a slight difference. Again, in reality, there is a slight attraction more to carbon than hydrogen in this case, but not considered enough to consider it a polar bond. It's still considered a non-polar bond. Any questions on that there? Now let's take a look at oxygen and sulfur. Oxygen is 3.5, sulfur is 2.5, right? So again, if we do our difference in electronegativity, that's a 3.5 minus a 2.5. That is a 1. Again, that's going to put us in this region here, and that would give this a polar bond. Again, the electrons would be hanging out heading towards the oxygen in this case. By the way, same thing here. They would be heading towards the oxygen in the case of the carbon and oxygen bond that's happening. Now let's take a look at carbon and sulfur. Carbon's value is 2.5. Sulfur's value is 2.5. Difference in electronegativity here would be 2.5 minus 2.5. That is 0. And that is a difference of 0, which is definitely a non-polar bond. So this is an important thing that sometimes can occur. Absolutely, like what we had with H2, F2, and things like that, those guys are going to always be non-polar because they're both the same element. This one demonstrates that you can have two different elements that have the same electronegativity value and actually will be non-polar as well. So not all the time that you have different elements will it be a polar bond. It is possible to have two different elements, as shown here with carbon and sulfur, to actually have the same electronegativity value. How does that happen? Well, if we kind of look at this periodic table, it is what is sometimes referred to as the diagonal rule. Here is carbon and here is sulfur. They are diagonal of each other. Carbon is further up, but sulfur is further to the right. So they cancel out their differences and actually end up with the same electronegativity value. You also see that if you look at nitrogen and diagonally chlorine, you also see that same electronegativity values. So there's a number of places where you get that sort of diagonal relationship, even like boron and diagonally down there to AS, where one may be higher up on the list, but one is further to the right, and they sort of cancel out their differences. So there are some situations where that can definitely occur. It is definitely a safe bet if they're both the same element, it's going to be non-polar. If they are not the same element, probably in most cases it will be a polar one, but it can definitely be a non-polar one. Now, let's talk about a few situations here to finish up talking about this here for right now. But a few situations where, you really don't necessarily need this table or these numbers, right? One situation is what we've been talking about here, which is, really if you're able to identify it as a metal and a non-metal, you really don't need, this table to help you determine that's an ionic bond. It's going to be an ionic bond. So really for ionic bonds, you don't necessarily need this table. You just need to be able to recognize those two things. One's a metal, one's a non-metal. Now, let's talk about, say, this bond here that we determined, hey, this is a polar bond, right? Well, we know the general trend on the periodic table is up and to the right is more electronegative, and down and to the left, it is least electronegative or less electronegative. When we look at, say, carbon and oxygen is actually in the same row. They're dead on in the same row. And what we see is oxygen is further to the right than carbon. And because they're in the same row, we should know that oxygen is, regardless of the value, we should know oxygen should be more electronegative than carbon. And we can make a pretty safe bet that that's going to be a polar bond without even having to use the actual table, because we know that they're in the same row. And because oxygen is further to the right, it has to be more electronegative. So you wouldn't even really need the values on these tables to help you make that determination. What about another one? Let's talk about oxygen and sulfur. Oxygen and sulfur, they're in the same group, right? They're in the same basically column. And what we see is going this way, oxygen is further up. And what we know is as we go up on the periodic table, it becomes more electronegative. So we can make a safe bet just knowing that oxygen is higher up in the group, that it should be more electronegative, and this guy should be a polar bond. So there are several situations, especially when you're comparing two things that are in the same period, or if you're comparing two things that are in the same group, that you really don't need these numbers at all. You could just use the general trend of electronegativity, and you could determine, well, if they're in the same group or in the same period, it's going to be probably a polar bond. And which one would be more electronegative is whichever one, again, is further to the right or whichever one is further up. And you wouldn't necessarily need the numbers to help you determine that. Any questions on that or using this table? Clearly, this table would be provided for you, or the numbers would be provided for you if you needed them to, for something on a quiz or an exam or something like that. If they're not provided to you, then you probably could just use the general trend and sort of figure it out. But if they are needed, they would obviously be provided for you. Any questions on how to use electronegativity values here to determine really what we're talking about here, just so we're clear? There's going to be two types of sort of polarity that we talk about when we talk about bonding. One is molecular polarity, but really what we're talking about here is what is sometimes referred to as bond polarity. And that is whether or not, just strictly speaking, between those two elements, based on electronegativity values, are these things going to share those electrons equally or unequally? And that's sort of what we're talking about here. Molecular polarity, as we'll talk about later, deals with the entire molecule as a whole. Are the electrons going to be shared equally or unequally? Any questions on any of that there? All right, we will lay it up here. And